ladies and gentlemen.
So let's talk linear versus exponential growth. So linear growth is something you're probably very familiar with. It is when you have a relationship where the output is increasing by a constant rate of change, aka we're kind of adding the same number over consecutive intervals, over the same amount of time. So if we look here at this relationship, we can see for every 60, we are adding 1 to the output. So that would be a linear relationship. The slope, the rate of change, would be the change in the output, which is the 1 to 2, over the input, which is 0 to 60. So that is how we get 2 minus 1 over 60 minus 0, which gives us that 1 over 60 that we see here in this linear equation. We can see that the rate of change is the 1 over 60, and we start, the initial value is 0. So again, we can find that rate of change in a linear relationship by dividing the change in the output over the change of the input. So an exponential relationship is when your output increases at a proportional rate and your input changes at a constant rate, meaning that the outputs are being multiplied by a number and the inputs are being added by a number. We can see that we're adding 60 for each of the inputs and we're multiplying by 2 for each of the outputs. How that looks in an equation is we can see the doubling of the output as the b value. We've talked about this a little bit in a prior video. The number being multiplied is what's being raised to the power. You could also see that rate at which the input changes is represented by the denominator of the exponent, which is a little bit weird. The last part is our starting value. When we have an input of 0, our output is what's being multiplied by this thing to a power. It's our initial value. So you can see for both of these equations, it's fairly simple about how they kind of grow. This is we add 1 for every 60 we have. Here we double for every 60 we have. We start at 1, we start at 1. So you can kind of see where each of those pieces come from. So if we're given a relationship and we're asked, is it linear, is it exponential? We can see, are we looking for a pattern of addition? Are we looking for a pattern of multiplication? And we can figure out where each of these parts go by looking at the pattern we're given. So if we look at this pattern here, we have a bird enthusiast who's imported 100 starling from England and released them in a park near their home. This table shows the population P over T years. So we can see that it started as the initial population of 100, and then it's growing. But I notice that it's not growing linearly. So if we look here, we've added 250, and then for the next step up, we're not adding 250 again. So this must not be linear. But is it exponential? Well, what would we multiply by? Well, I can clearly see that this would be multiplication by 3.5. We have 300s and half of 100. But is this 350 times 3.5? Let's try it out. So 350 times 3.5. Well, 3 times 350, well, 2 350s would be 700. Another 350 on top of that would be 1,050. Then we want half of it that we're going to add to it. Half of 300 is 150. Half of 50 is 25. 150 plus 25 is 175. And this 50 and 75 would end up making a 25, increasing the 100 by 1. So we do get that value. So it seems like the pattern is multiplication by 3.5. That pattern seems to hold. You can check me with a calculator, do it yourself to see if the 4,287 works out. So what is that formula? Well, it seems like we had a starting population of 100, and that we are multiplying each of these values by 3.5. So 3.5 is going to go in its parentheses, and it's going to get to the power of x. Now, does it get a denominator? If we notice in the example I had up here, we had a denominator. That denominator was 60. But look at the inputs. The inputs were increasing by 60 every time I looked at it. For this one, they're increasing by 1. So we do not need a denominator. So our function here, essentially, is p of t is equal to 100 times 3.5 to the power of not x, but it needs to be t. That's not that bad. How many starling would there be in the area at the end of 10 years? Now that gets a little complicated. We do p of 10, which is equal to 100 times 3.5 to the 10 power. Now, if you're given a question like this, you're probably going to be given a calculator to go along with it. You can multiply 3.5 by itself 10 times and then multiply by 100 and see what happens. But in this case, I'm going to cheat a little bit and I'm going to pull up a calculator. So if we have a calculator, we can easily do 100 parentheses 3.5 and raise that to the power of 10. And we get quite a large number. Very difficult to do by hand, but possible. We get 275,85473.54. So we get 27,585,473.54. So in a question like this, I would always round up. If you have more than a little bit of something, you would always round that up. You can't have 0.54 of a sterling. You can't have 0.54 of a person. So got to use your context clues and see, should you round up, should you round down? In this case, if you're talking about a population of something, I would almost always round up. So that is our answer. Now, if I were to leave it like that, I would probably yell at my students. We are talking about starlings. So that is what we're going to use as our unit. Probably not as important on a standardized test, but important if you're dealing with a situation to figure out what your number actually means. That is it for this. If we have any questions, let me know. Otherwise, I'll see you in the next video.